Hello, this is Guillermo Campitelli, and in this video I'm going to briefly explain the maximum likelihood approach to model comparison. Okay, so in the previous approach, the error minimization approach, which the idea is to minimize the predictive error, so the error of the prediction. What we did is to compare the actual value of the dependent variable, in this case academic achievement, and the value that was predicted by the model. So we subtracted all the predicted value and the actual value, and we obtained a sum of errors or squared errors. In the maximizing the likelihood approach, instead of determining what's the difference between the prediction and the actual value, we determine how likely is to obtain the actual value in a probability distribution, in some probability distribution. Typically we use a normal distribution, but any other distribution can be used, and sometimes it's more appropriate to use other distributions. Okay, so let's show an example using model 1. So model 1, we've got beta 0 plus beta 1 times study hours, and that would be equal the mu, so our prediction of academic achievement. So I have here I'm showing three graphs. In these three graphs, the mu is different, so mu 50 in the top, mu 55 in the middle, mu 60 in the bottom. The sigma is 5 in the three cases. And so basically this is a normal distribution with mu 50 and sigma 5. This is a normal distribution with mu 55 and sigma 5. So this is a normal distribution with mu 60 and sigma 5. Now, the mu, remember, comes from the formula of model 1, which involves study hours. So basically, based on the parameter estimation, so the values, the best values for parameters beta 0 and beta 1, and a value of study hours 22 would give a prediction of academic achievement of 50. So if someone with 22, the prediction of the model is that the academic achievement would be 50. Okay, so if we use the normal distribution with the prediction as mean, and in this case we use a sigma of 5, but I'm going to explain that we can change that. So basically, if the actual value is 50, then the likelihood of that value is high. But if the value is 85, the likelihood of that value is very small in this distribution. Similar, if we get a 20, the likelihood is very small. Okay, so basically, instead of calculating the difference between the prediction and the actual value, we calculate what's the probability of obtaining the actual value in a distribution in which the mean is our predicted value and we have some standard deviation. Okay, so this is similar as before, but like in this one, if the mu is 55, so that corresponds to study hours of 30, and if we obtain the value 50, then it has less likelihood than in this distribution. Okay, so basically we have to come up with a model that produces mu that are as close as possible as the actual value, and then the sigma here I fix it in to 5, but in the actual maximum likelihood approach, this is actually estimated as well. Well, you may ask, well, why don't we have a larger sigma? So larger sigma would make the curve flatter. So if we get a value very far from the predicted value, it still has a higher likelihood than it's not as low likelihood as in this case. Well, that's correct, but the problem is that if we get a value close to the predicted value, so if our prediction is quite good, then the likelihood of that value will not be as high as in this case. So basically the sigma should be as small as possible, so the likelihood of the values that are close to the predicted value is higher. So we want the highest likelihood possible. So we have to come up with parameters for beta 0 and beta 1 that will produce a mu which is as close as possible to the actual value, and the sigma, and we use only one sigma for the 300 predictions. We don't use a different sigma for each prediction. So the sigma we also want it as small as possible to provide high likelihood to the values that are close to the predicted value, but it could be a bit higher or a bit lower in order to get the most the highest likelihood of the whole model. Because what we are going to do is that for each value we are going to establish what's the likelihood of that value. Okay, so basically we have a predicted value for each participant. This is a mu for each participant. We have an actual score for each participant. We measure that. Instead of calculating the difference, as in the error minimization approach, we calculate the likelihood of the actual score given the predicted value. So now we have 300 likelihoods. Now what we can do is to obtain the likelihood of the whole model by multiplying those 300 likelihoods. So the likelihoods are like probabilities. Remember probability theory that we saw in previous videos, the product rule. In the product rule, the probability of two events is the product of the probability of each of those events. So what's the probability of obtaining two scores? Well, it's probability of obtaining one score times the probability of obtaining the other score. So when we multiply, remember probabilities, if we use probability mass, then they will be numbers between 0 and 1. If we use probability density, could be numbers higher than 1. But typically the values are low, and when you multiply values lower than 1, and you get even lower numbers. So sometimes dealing with the likelihoods is complicated because they are very, very low numbers. So when you multiply 300 likelihoods, the number could be very, very small. So a trick in order to deal with that problem is to use log likelihoods instead of likelihoods. And log likelihoods is the logarithm, is obtaining the logarithm of the likelihood. And a nice feature of that is that instead of having very small values, we are going to have higher values. But the good feature is that instead of it turns out that adding log likelihoods is equivalent to multiplying likelihoods. So instead of using multiplication, you have to use addition. So it's a bit simpler to deal with. So I'm going to show you examples of likelihood. As I said, if we are dealing with probability mass, the maximum value is 1 and the minimum is 0. but in probability density the minimum is 0, but it could be more than 1. So if the values are between 0 and 1, then when we obtain the log of those values, the logarithm of those values, it will be values between 0 and minus infinity, so there will be negative numbers. But we have some likelihoods that are higher than 1, so some log likelihoods will be higher than 0 as well. Okay, so these are examples. The likelihood, the logarithm of 1 is 0, the logarithm of 0.5 is minus 0.693, the logarithm of 0.1 is minus 2.303, etc., etc., etc. So you can see that now it is becoming a very small number, but here we got minus 11, so it's more manageable. Now remember, I told you that multiplying likelihoods is equivalent to adding log likelihoods. So if you see this case, if you multiply 0.1 times 0.01, so these two, then you obtain 0.001. Yeah, simple. Now let's add the equivalent log likelihood. So instead of 0.1, we use the log likelihood minus 2.303, and instead of 0.01, we use the log likelihood minus 4.605. So instead of multiplying and obtaining this value, we are going to add those values, and you'll see that we are going to obtain this one. So minus 2.303 plus minus 4.605 equals minus 6.908. So you can corroborate that when you multiply likelihoods, and if you use the corresponding log likelihoods, you need to add and you obtain the corresponding log likelihood of the two likelihoods that you multiplied. Okay, so this is just mathematics, and we are not going to deal much with that, but I like to show you why we use log likelihoods instead of likelihoods. Okay, so another statistic is called the deviance. Now the deviance, basically what you do is minus 2 times the log likelihood. And why do we do that? I think the main reason of that is that instead of the log likelihoods typically are negative numbers. Could be the case to be positive if we have very high densities, which are more than 1, but typically they are negative numbers. So if you multiply the negative number by a negative number, you will get a positive number. So dealing with negative numbers is a bit cumbersome. So with the deviance we have positive numbers. So we use log likelihood instead of likelihood to have not too small numbers, and we then multiply by minus 2 to have positive numbers. Okay, so now the a note that is important: some software use a different formula of deviance. I'm not going to explain the difference between this formula and the other formula. They are for different things, but basically they report another deviance. Now the most important aspect is that after the deviance we are going to calculate the AIC, and I'm going to show what AIC is in a second, and just concentrating the AIC because the deviance sometimes is reported in different ways. Okay, so the next slide is the AIC. AIC stands for Archaic Information Criterion, and basically is the deviance plus 2 times k, where k is the number of parameters of the model. So basically, the AIC takes into account the likelihood, and then it penalizes for having too many parameters. So basically, the lower the AIC, the better. And if so, what you want to have is a low deviance. That is, that the lower the deviance, the best the prediction of the model. And you want to have the least number of parameters in the model, because if you have too many parameters, it will increase the AIC, and we want a low AIC. So the lower the AIC, the better the model. So basically, remember that when in the previous approach, we had the R-square and then the adjusted R-square, and the adjusted R-square penalized for having parameters. So same thing here. The deviance will tell us how, or the log likelihood of the model will tell us how well the model is fitting the data, but the AIC penalizes for having a model which is too complex with too many parameters. Okay, so basically, how do we interpret the AIC, the archaic information criterion? By the way, it's not the only possibility. There is the BIC, which is the Bayesian information criterion, and there are many other options, but AIC is quite standard. Okay, so how is interpreted the AIC? A difference between 0 and 2 between models. So we are going to compare the AIC of of two models, and the difference between 0 and 2 is considered only anecdotal evidence for the model with lower AIC. A difference between 2 and 6 is considered positive evidence for the model with lower AIC. A difference between 6 and 10 is considered strong evidence for the model with lower AIC. And a difference greater than 10 is considered very strong evidence for the model with lower AIC. Okay, so let's see. In our case, we have model 0, model 1, model 2, model 3, and model 4. And here we've got the parameters that were estimated. In model 0, only beta 0 was estimated. Model 1, beta 0 and beta 1. Model 2, beta 0 and beta 2. Model 3, beta 0, beta 1, and beta 2. And model 4, only beta 0 and beta 3. So these are the values of the parameters that were estimated. So so they are the best values that will increase the likelihood of the model. So here is the log likelihood of each of the models, and here we highlight that model 3 is the model with the higher value. We are using negative numbers, so this is the higher value, and the deviance transforms this into positive numbers. So basically, we want the lower value of deviance. So we want the highest likelihood or log likelihood, but we want a lower deviance. So the deviance is lower. The lowest deviance is in model 3, and AIC we penalize for models. So you can see that the model 3 went to 1672 to 1678, so it increased 6 points, whereas the model 4, it increased from 1678 to 1682. So basically only 4 points, and that's because it has one less parameter, 1, 2 versus 1, 2, and 3. So as you can see, Model 3 has the lowest AIC, and is very and this is the important aspect of maximum likelihood estimation. When we come up with the AIC of each model, we can compare the AIC of any model. Remember that in the previous case, we were only able to compare the nested models. Non-nested models were impossible to compare. Here we can compare any model. We just have the AIC, and whichever has the lowest value is a better model. Now, Model 3 and Model 4 are much better than the other models. There is very strong evidence, but the difference between Model 3 and Model 4 is only 4 points. So there is some evidence in favor of Model 3, but it's not very strong, the evidence. So Model 3 and Model 4 are much better than the others, and Model 3 slightly better than Model 4. Okay, so this finishes the maximum likelihood approach. In the next video I'm going to explain the Bayes factor approach.